Okay, Bismillahirrahmanirrahim. Welcome to the second part of this week's lecture of digital communication. Once again, I would like to remind you that there are a lot of concepts and theoretical knowledge involved in this part of the course. So normally we would be writing these things on the board and you would be copying them down in your notebooks or registers. However, you are still encouraged to write and make notes as you listen through these lectures. It is very important that you are writing them because otherwise you will find it difficult to understand and absorb them. Okay, so coming over to this week's topics, these are the topics that we have covered in the previous part of the lecture, and these are the topics that inshallah we will cover in this part of the lecture. And considering that we might have a bit of a time left, we might actually go on and cover these topics as well in today's remaining lecture. So once again, showing you the learning outcomes from this week's classes, which are based on the core topics from this week's classes. We might be studying a couple of topics more than what we had planned, but these relate to the topics originally part of the weekly plan. Okay, so let us quickly recap the phasor representation of a sinusoid. We are well conversant with a very well known trigonometric identity called Euler's theorem, through which we introduce the complex notation of a sinusoidal carrier wave, which we know is represented e raised to power j omega naught, which is equal to cos of omega naught t plus j sine of omega naught t. So basically we can represent our e raised to power j omega naught t as consisting of two parts, a real part and an imaginary part. The real part is cosine and the imaginary part is sine. Normally we indicate it by j. Please don't mind the writing. It's very difficult to use this touchpad to write. So this is the Euler's theorem. We know that. So why we use this? And that is how the the sinusoid is represented as a phasor. So why we use this notation? Because this notation, it facilitates our description of how real world modulators and demodulators are implemented. So the benefits of viewing our carrier wave in the complex form: first of all, within this compact form, e raised to power j omega naught t is contained the two important quadrature components of any sinusoidal carrier wave, namely the in phase or the real component here in this direction, and the quadrature or the imaginary component that is in this direction, and they are both orthogonal to each other. So that's the first advantage or benefit. Secondly, we can represent our unmodulated carrier wave conveniently in a polar coordinate system as a unit vector or phasor rotating counterclockwise at the constant rate of omega naught radians per second, as you can see in this figure. So we can consider it as a vector which is rotating at omega naught radians per second. and as you can see in the figure, as time is increasing, that is from t0 to t1, we can visualize the time varying projections of the rotating phasor on the in phase axis and on the quadrature axis. So these Cartesian axes, they are usually referred to as the I channel and the Q channel respectively. We know that we have seen the IQ plots or the IQ diagrams, and the projections on them, they represent the signal components which are orthogonal to each other. So that's the other benefit. We can have a look at the unmodulated carrier. And thirdly, when it comes time to modulate the carrier wave with information, we can view this modulation as a systematic variation of the rotating phasor and its projections. So you see, these are the benefits of representing sinusoids as a phasor, because we can graphically visualize them. Okay, so having just quickly revised that we can represent our sinusoid as a phasor, we will go on to look at this important concept of decision regions. So we consider a two-dimensional signal space as shown here in this figure, and it is basically shown in the figure is the locus of the binary vectors disturbed by noise. So let us say that we have the original binary vectors S1 and S2. This is the original vector because we are dealing with the binary data, so we consider these two vectors. So this vector represents one form of binary and this represents the other form of binary. So these are our original binary vectors, and then you can see them getting disturbed by noise. So you see a scatter around this vector. So the undisturbed position or the original amplitude and phase of this vector should be this point here, and the original amplitude and phase of this vector should be this point here. However, you can see that this value doesn't remain the same because of the addition of noise. In fact, it is scattered around this point, as you can see the tiny scatter dots. So these are our basically scatter values of S2 plus n, and these are the scatter values of S1 plus n, where n represents our noise or noise vector, and that is a zero mean random vector. So because of the noise, we will have a received signal vector R for received signal vector, that will also become a random vector with the mean of either S1 or S2. So after all this scenario, I mean, these are the actual vectors, but because of disturbances we might be actually getting this. It's neither really S1 nor really S2. So what is the task of the detector? So after it receives R, the task of the detector is to decide which of the signals, S1 or S2, which of them was actually transmitted. So the method is usually to decide on the signal classification that yields the minimum expected probability of error. So for example, for the case where S1 and S2 are equally likely, and if the noise is AWGN, the minimum error decision rule is equivalent to choosing the signal class such that the distance of the received vector from the original vectors, the distance is minimized. So one distance is this, indicated by R minus S1, and the other distance of the received vector from the original possible positions of vectors is this. So we have these two distances, and based on the minimal distance, the receiver or the detector that will make a decision. So this rule is often stated in terms of the decision regions. So this is, as you can see in the figure, what we have are the decision regions. So there is a line that has been drawn connecting the tips of the prototype vectors S1 and S2. Okay? This line, which connects the tips of the original prototype vectors S1 and S2, and then we draw or construct the perpendicular bisector of the connecting line. So we draw its perpendicular bisector. Please notice that this bisector passes through the origin of the space. If S1 and S2 are equal in amplitude, they are, so they differ only in phase. So when they are equal in amplitude, this bisector will pass through the origin. So in this example, the constructed perpendicular bisector that represents the locus of the points, this represents the locus of the points which are at the same distance from S1 and S2. So hence this bisector, it acts or describes as the boundary between decision region 1, here this all is decision region 1, and this is decision region 2. And then once you have the decision regions, so the decision rule for the detector, if we want to state it in terms of decision regions, that will be as follows: that whenever the received signal R is located in region 1, it will choose signal S1, whereas when it is located in region 2, it will choose signal S2. So in this figure, if the angle theta, for example, equals 180 degrees, then the signal set S1 and S2, they represent BPSK. But this is an example, so the angle theta was chosen less than 180 degrees. So this is the concept of decision regions as we will apply to signal vectors when we are analyzing them. Okay, so let us quickly consider the variance of white noise. We know that white noise is an idealized process with two-sided power spectral density which is equal to a constant and not by 2 for all frequencies from minus infinity to plus infinity. So hence the noise variance, since the noise is 0 mean, so the noise variance for the average noise power, that is basically infinite. That is infinite. That's what we discussed previously as well. So although the variance for AWGN is infinite, the variance of filtered AWGN is not so infinite. It is a finite value. So from here onward, we will assume that the noise of interest in the detection process, in fact it is finite and it is equal to n naught by 2. So we will assume that the noise of interest in detection process, it has a variance of n naught by 2. So that's what we need to remember with reference to AWGN. So now we come over to the basic SNR parameter for digital communication systems. We know we have studied communication systems in the previous semester, so we are well familiar with the term signal to noise ratio, S by N or SNR, and which can be broadly defined as the average signal power, the ratio of average signal power to the average noise power. But in digital communications, we more often we use EB by N naught, which is a normalized version of SNR, and that is the figure of merit that is used in digital communication. And here EB represents the bit energy, which can be described as the signal power S multiplied by the bit duration TB or the bit time TB. So that is how we can get the value of the bit energy, the power multiplied by its duration, which is a normal formula for calculating energy. So in this scenario here, N naught represents the noise power spectral density, and power spectral density can be calculated or can be described as the noise power n divided by bandwidth w. So n by w. So now you have to remember that the bit duration and the bit rate, they are reciprocals of each other. So if we put the values in for EP by n naught, so instead of EP we will use S multiplied by TB, and for n naught we will use n divided by W. n divided by W. So n naught की जगह हमने n naught लगा ली उसकी वैल्यू n by W ये, और EB की जगह हमने लगा लिया S multiplied by TB ये, ठीक है। एंड जैसे मैं जिक्र कर रहा था कि बिट रेट और बिट टाइम एक दूसरे के रेसिप्रोकल है, तो वी कैन एक्चुअली यूज़ बिट रेट इंस्टेड ऑफ बिट ड्यूरेशन या बिट टाइम, ठीक है। तो फिर हमारे पास इक्वेशन जो है वो बदल जाएगी, ये हो जाएगी ये भी बाय नॉट की, ठीक है, ये होगी। इसके बाद हम ये देखते हैं कि ज़्यादातर डेटा रेट इन यूनिट्स ऑफ बिट्स पर सेकेंड, because that is one of the most frequently used parameters in digital communication। तो नोटेशन को सिंप्लीफाई करने के लिए हम RB की जगह R यूज़ कर लेंगे टू इंडिकेट द बिट रेट और द डेटा रेट टू रिप्रेजेंट बिट्स पर सेकेंड। तो इस इक्वेशन को हम रीराइट कर लेंगे, तो इसमें हम बजाय RB लिखने के इसको R लिख देंगे, थोड़ा सा इसे रीअरेंज कर लेंगे, EB बाय नोट जो है इस फॉर्म में आ जाएगा बेसिकली। तो S बाय N मल्टीप्लाइड बाय W बाय R। तो ये तो हमने शुरू में बात की थी कि EB by नोट और कुछ नहीं है, सो दैट इज़ बेसिकली अ वर्जन ऑफ सिग्नल टू नॉइज़ रेशो S by N which has been normalized by bandwidth and bit rate, ठीक है, ये हमें ध्यान में रखना है। तो इट इज़ जस्ट अ नॉर्मलाइज्ड वर्जन ऑफ S by N। So one of the most important metrics of performance in digital communication systems is usually a plot of the bit error probability PB versus EB by naught। तो EB by naught जो है it can be considered as a metric that characterizes the performance of one system versus other। तो दोनों की हम परफॉर्मेंस मेज़र कर सकते हैं EB by naught के ज़रिए। क्या चीज़ ध्यान में रखी है कि स्मॉलर इज़ द रिक्वायर्ड EB by naught for a certain probability of bit error, the more efficient is the detection process of that particular communication system। तो ये वो तस्वीर है जो हमने पहले भी देखी हुई है। तो बेसिकली डिजिटल कम्युनिकेशन सिस्टम में instead of S and R we have the EB by naught on X axis and we have the probability of bit error on Y axis। एनालॉग में ये probability थी और यहाँ पे S and R था, तो डिजिटल में ये EB by naught। So now we come over to the important issue of detection of binary signals in Gaussian noise, and for that matter we will refer to this conditional PDF figure that we have discussed previously, as you can see here। And first of all we will be talking about the maximum likelihood receiver structure। So when we discussed this we mentioned that there is a decision making criteria which was defined by this equation here। So when we take the sample of the pulse, that sample is compared to a threshold, and based on this comparison, if the sample value is greater than this threshold gamma, we go for hypothesis H1, and if it is less than this gamma, we go for hypothesis H2। So a popular criterion for choosing the threshold level gamma for the binary decision in this equation is based on minimizing the probability of error, what we discussed previously। So the calculation of this minimum error value for gamma is equal to gamma naught, it starts with forming an inequality expression। So the value for gamma, it starts with forming an inequality expression between the ratio of conditional probability density functions and the ratio of the signal a priori probabilities। So these are two ratios. One ratio is that of conditional PDFs and the other ratio is that of the signal probabilities that are known beforehand. So this is the ratio we are talking about. So that is the ratio of the conditional probability density functions, and that is the ratio of the a priori probabilities. So this is what we use in our effort to try to come up with a value of gamma. So this formulation, this is also called the likelihood ratio test. So in this inequality, P of S1 and P of S2, they are the a priori probabilities that S1 of t and S2 of t respectively are transmitted, and H1 and H2 are the two possible hypotheses. So the rule for minimizing the error probability states that we should choose hypothesis H1 if the ratio of likelihoods is greater than the ratio of a priori probabilities. So if this ratio is greater than this ratio, we'll go for H1, otherwise we'll go for H2. So for example, if we consider that both the probabilities are equal, yes, if P of S1 is equal to P of S2, and if the likelihoods, if these conditional PDFs they are symmetrical, then the expression for Z of t, this expression here, basically it translates into this, where A1 is the signal component of Z of t. A1 is the signal component. Remember, Z of t had a signal component and a noise component. So here we are talking about signal component. So A1 is the signal component of Z of t when S1 of t is transmitted, and A2 is the signal component of Z of t when S2 is transmitted. So the threshold level gamma naught, which is represented by the average value of A1 and A2, that is the optimum threshold. That is the optimum threshold for minimizing the probability of making an incorrect decision for this important special case. So this strategy is known as the minimum error criterion. So what will happen? The detector will choose S1 if for any particular point P of ZA given S1 is greater than P of ZA given S2. So for equally likely signals, yes, so that means that P of S1 is equal to P of S2. So the optimum threshold gamma naught passes through the intersection of the likelihood functions as shown in the figure. Gamma naught it passes through the intersection, this intersection here. So the decision state effectively selects the hypothesis that corresponds to the signal with the maximum likelihood. So for example, in this figure, given an arbitrary detector output value ZA of t, let us say this is the value we got, ZA of t here, for which there is no non-zero likelihood that ZA of t belongs to either signal class S1 or S2 of t. So one can think of the likelihood test as a comparison of the likelihood values P of ZA given S1 and P of ZA given S2. So the signal corresponding to the maximum PDF is chosen as the most likely to have been transmitted. So in other words, what we are saying, I am repeating, that the detector will choose S1 if the value on this curve, is greater than the value on this curve. So if you notice here now, what will be the situation? So if that's not the case, if this is not greater than this, then the detector will choose S2 of t. So a detector that minimizes the error probability for the case where the signal classes are equally likely or their probabilities are equal. So that detector is known as maximum likelihood detector. So we can arrive at it with common sense as well. So if you got this value here of sample, yeah, and you can see that it is closer to this as compared to this. That is a common sense way of making a decision anyways. So given the detector output ZA of t, we can see in the figure that the ZA of t, it intersects the likelihood of S1t. It intersects the likelihood of S1 of t at this level called L1, and it intersects the likelihood of S2 of t at a value L2 of t, L2 here. So what do you think will be the most reasonable decision for the detector to make? So in this example, choosing class S1 of t, which has a greater likelihood, is the most sensible choice. So as you can see that because the value here is greater, it will go for the decision in favor of S1 of t. So as I said, if L2 was greater, then it would have chosen S2 of t. So that is how the binary signals are detected in the presence of noise. That is what we need to remember. And now let us go on to look at the error probability. So once again we are referring to the same curve. So for the binary decision making, as depicted in this figure, there are two ways then error can occur. Okay, so error E will occur when S1 of t is sent, and the sample value we take, Z of t, that is less than gamma naught due to channel noise. So now that becomes a conditional probability of error, because we sent S1, we say the probability of error given S1. Okay, so we say that what is the probability of error given that S1 was sent. So when will that happen? When our sample value is less than gamma naught. So in this scenario, what basically will happen is that we will select hypothesis H2. So when will error occur? When we select hypothesis H2 given that S1 was sent. And what is the value of that? Well, according to the figure here, that is basically represented by this shaded portion here. So the probability of error is indicated by this shaded portion here. So the integral from minus infinity, the integral of this curve up to gamma naught value. So we are trying to find that value here, this shaded. This gives us the probability of error given that S1 was sent. Because up until this moment, if our sample value is for example not here, if our sample value is here, and we once again try to look at N1 and L2, so here our this curve, S1 curve, will give us this value, and S2 curve will give us this value. So because the value of S2 curve will be greater than S1 curve, so it will decide in favor of S2, which will be wrong, which will be an error. So when will that error happen? As long as the L2 value is greater than L1, it will keep making those errors. So all this way up until here, this is where actually when L1 and L2 will be equal at this point. And beyond that, L1 will be greater than L2. So then the probability of error decreases. So as I said, this thing here, that is illustrated by the shaded area to the left of gamma naught in this figure. So similarly, an error occurs when S2 of t is sent and the channel noise results in Z of t being greater than gamma naught. So the probability of this occurrence, probability of error given S2 was transmitted, that is the same as saying that we select hypothesis H1 given that S2 was sent, and that will be equal to integral of a shaded portion of this part here, this part here. So that's what you need to remember. So these integrals basically, or this shaded area, they give us the probability of conditional probabilities of error. So you might have studied in probability theory that if an event A is conditionalized on different events, so the probability of the event A is the sum of all the conditional probabilities. So here probability of bit error PB, the probability of an error, that will be the sum of the probabilities of all the ways that an error can occur. So here we can represent P of B. For the binary case, we can express the probability of bit error as the sum of these two probabilities of errors. So basically here we have the sum of them. So substituting their equivalent values, that is what we get for the probability of bit error. And then in terms of hypothesis, this is the equation we get. So that is, given that the signal S1 was transmitted, an error results if hypothesis S2 is chosen, or given that signal S2 was transmitted, an error results if hypothesis H1 is chosen. So for the case where the a priori probabilities are equal, this can become simplified. So it translates into this, and if the probability density functions are symmetric, then basically this is equal to this, because the shaded area is the same. So the probability of a bit error PB, that is numerically equal to the area under a tail of either likelihood function falling on the incorrect side of the threshold. Okay, so we can therefore compute the probability of bit error by integrating this curve between the limits minus infinity to gamma naught, or by integrating this curve between the limits gamma naught and infinity. We can calculate probability of bit error from either of the curves. For example, here it's shown. So here the gamma naught is taken as the average of A1 and A2, and which is the optimum threshold. So if we replace the conditional probability of Z given S2 with its Gaussian equivalent from equation 3.6 we studied earlier, so that is what we get, the probability of bit error, and in the general equation of Gaussian probability density function, that is what we get. So we can get the probability of bit error directly from the equation of the Gaussian distribution. So that's what you need to remember. So that is how we calculate the probability of bit errors for the binary case. Okay, so now coming over to matched filter, the concept of matched filter. This figure will be our reference. You've seen that before. That is the demodulation and detector stage in the receiver. So basically a matched filter is a linear filter designed to provide the maximum signal to noise ratio or signal to noise power ratio at its output for a given transmitted symbol waveform. So we want to make an assumption here. We consider that a known signal S of t plus AWG and N of t that acts as an input to an LTI filter, a receiver filter, this followed by a sampler as shown in the figure. So at time t is equal to capital T, the sampler output Z of t here, this, it consists of a signal component AI, we've done that earlier, and a noise component N naught. So at that point, if we want to calculate the value of signal to noise ratio at that time, so the variance of the output noise will be the average noise power, that can be denoted by sigma naught square, and then in that case the ratio of the instantaneous signal power, so the signal power at time t is equal to capital T, to the average noise power, at the output of the sampler. That will be given by here AI square divided by sigma naught square. So that will be the signal to noise ratio at time t is equal to capital T. So now we wish to find the filter transfer function S naught of f such that which maximizes this signal to noise ratio. So the value of AI of t that we get at the filter output, we can express it in terms of the filter transfer function h of f and the Fourier transform of the input signal. So basically we can represent AI of t here, so the value of the signal power here as this, where S of f is the Fourier transform of the input signal, S of t का Fourier transform S of f, और h of f जो है वो ट्रांसफर फंक्शन है. So if the two-sided power spectral density of the input noise is n naught by 2, तो हम फिर नॉइज़ की पावर भी निकाल सकते हैं. ठीक है. सो आउटपुट नॉइज़ की जो पावर होगी वो सिग्मा नॉट स्क्वायर बाय 2 होगी एंड दैट इज़ बेसिकली गिवन बाय दिस. तो वो जो नॉइज़ उसमें सिस्टम में एंटर हो रही है उसकी नॉइज़ पावर इतनी होगी. सो वी हैव गॉट द एक्सप्रेशन फॉर ए आई एंड वी हैव गॉट द एक्सप्रेशन फॉर सिग्मा नॉट स्क्वायर. ठीक है. तो अगर मैं सिग्नल टू नॉइज़ रेशो निकालना चाहूँ एट टाइम टी, तो वो क्या होगा, बेसिकली इसको स्क्वायर कर लूँगा. ठीक है. इसको स्क्वायर कर लूँगा, इसका स्क्वायर ये हो जाएगा और नीचे जो है ये आ जाएगा. तो ये मेरा सिग्नल टू नॉइज़ रेशो बन रहा है एट टाइम टी. तो ये मेरे पास ये एक्सप्रेशन आ गया. अब क्या करना है नेक्स्ट, we next want find that value of HF equal to S naught of F for which the maximum signal to noise ratio at time t is achieved. तो यहाँ हम इसको मालूम करने के लिए हम यूज़ करेंगे शॉर्ट्स इनइक्वालिटी. और शॉर्ट्स इनइक्वालिटी क्या कहती है, बेसिकली वो ये कहती है कि अगर दो फंक्शंस आपस में मल्टीप्लाई हो रहे हो और उनका हम इंटीग्रल ले रहे हो स्क्वायर, तो दैट इज़ बेसिकली लेस देन और इक्वल टू, अगर हम दोनों को स्प्लिट कर दें, उन दोनों को हम स्प्लिट कर दें. सो दिस इक्वालिटी होल्ड्स इफ f1 of x इज़ अ लीनियर फंक्शन ऑफ f2 of x ऑफ द कॉम्प्लेक्स कॉन्जुगेट. ठीक है. तो अगर हम ये चीज़ इस पर अप्लाई करें, लेट्स से कि h of f जो है हमारा वो बेसिकली f1 of x है और s of f जो है वो मल्टीप्लाइड बाय द एक्सपोनेंशियल ये हमारा f2 of x है. तो फिर हम अपने इस एक्सप्रेशन को इस तरह से लिख सकते हैं. तो अगर हम उसी इक्वेशन में जो कि अभी हमने डिराइव की है एस सिग्नल टू नॉइज़ रेशो एट टाइम टी, उसमें अगर हम सब्स्टिट्यूट करें तो हमारे पास, हम इसको सब्स्टिट्यूट कर देंगे, फिर कोई कैंसिलेशन के बाद हमारे पास ये रह जाएगा. ठीक है. और ये जो है बेसिकली दिस रिप्रेजेंट्स द एनर्जी ऑफ द इनपुट सिग्नल, ये एनर्जी का फार्मूला. तो ये हमारे पास मैक्सिमम एस एन आर जो है वो 2E/n0 हो जाएगा, जैसे आपको यहाँ पे नज़र आ रहा है. तो यहाँ से हमें क्या पता चलता है कि द मैक्सिमम आउटपुट सिग्नल टू नॉइज़ रेशो एट टाइम टी डिपेंड्स ऑन द इनपुट सिग्नल एनर्जी एंड द पावर स्पेक्ट्रल डेंसिटी ऑफ द नॉइज़. दैट इज़ व्हाट वी नीड टू रिमेंबर. और एक कंडीशन ऑफ इक्वालिटी है कि ये तो द कंडीशन ऑफ इक्वालिटी इन इक्वेशन 3.52 कब इसके इक्वल होगा, that will hold only if the optimum filter transfer characteristic S naught of f वो जो है वो एक distortionless system के बराबर हो. So if we have a distortionless system, तो फिर अगर हमारा जो सिस्टम का जो इम्पल्स रिस्पॉन्स है यानी कि वो कुछ इस तरह का हो कि जी हमारे पास जो आउटपुट इम्पल्स रिस्पॉन्स जो है वो मैसेज सिग्नल हो, उसका कोई एक स्केल्ड वर्जन हो और डिलेड बाय सिंपल ड्यूरेशन, तो तब हमारे पास इसकी मैक्सिमम वैल्यू आएगी, इक्वालिटी इसकी तब आएगी. तो वरना ये लेस देन और इक्वल टू होगा. तो बेसिकली दैट वाज दिस वीक्स लेक्चर ऑन डिजिटल कम्युनिकेशन. हमने इसमें मुख्तलिफ टॉपिक्स पढ़े लेकिन दैट इज़ हाउ दे आर ऑल इंटरकनेक्टेड टू ईच अदर। तो बेसिकली सारा जो है फोकस इस वीक को इस चीज़ पे था कि अगर हमारे पास एक नॉइज़ अफेक्टेड सिग्नल आ रहा है तो कैसे हम उसे रिट्रीव करेंगे, रिसीवर में क्या प्रोसेसेस चल रहे होते हैं, और हमारा टारगेट क्या है मैच फ़िल्टर को लेके। सो वी यूज़ अ मैच फ़िल्टर जिसका काम ही होता है कि हमें मैक्सिमम SNR दे दे। तो कुछ मैक्सिमम SNR लाने की कुछ कंडीशंस होंगी, तो जिस वक्त हम सैंपल ले रहे हैं उस वक्त हमें मैक्सिमम SNR चाहिए। और जैसा हमने आखिर में एक्सप्रेशन देखा कि मैक्सिमम SNR डिपेंड्स ऑन द इनपुट सिग्नल एनर्जी एंड द पावर स्पेक्ट्रल डेंसिटी ऑफ नॉइस, तो उसी से डिसाइड होगा। थैंक यू वेरी मच, दैट्स इट फॉर दिस वीक्स लेक्चर।